Okay, so let's start with the graph. We can make it random, like this. So if we were to find the area of um, everything under this graph, so all of this, let's end the graph at here. So what we would need to do is actually draw a lot of rectangles. So for example, it would just be a lot of rectangles like this. And you see how my rectangles are actually above the curve, so it's not a very accurate representation. However, let's say I had an infinite amount of these rectangles, and let n be equal to the number of rectangles. So then I would have n to infinity rectangles, so let that be a limit. This is just basically saying as n approaches infinity, well, I would have an infinite amount of rectangles. Okay, so our second step. Let's define this function as f of x. And let us define I as a starting point. So, then we would create a function called f of x of I that represents the height of every rectangle. So, here is f of x of I at a specific point, that is. Now, to find the area of every single one of these rectangles, assuming that they all have the same width, we let this be the change of x. And in calculus, well, we can set that to dx. Now, the area of every single rectangle is f(x) of I, depending on what I is, times the change of x. So let's write that in our formula. Whoops. Times the x. So this here represents the individual rectangles. Now we need a summation formula that tells us to sum every rectangle that we have. So if this is the formula for the for the area of one rectangle, then we create a summation from n rectangles, or from here, n is infinity. Hither we have n rectangles, and we start at I equals 1, which we said was our starting point. This just means that there are n rectangles in total, and here is the area of every individual rectangle. And then we sum all of those rectangles to get the Riemann sum. Let me just explain one more time that this only means that there's n rectangles. If I was, for example, 0, then there would be n plus 1 rectangles. However, that is how you get the Riemann sum formula. Thank you.